modern natural science, which alone has achieved an all-round systematic and scientific development, as contrasted with the brilliant natural philosophical innovations of antiquity and the extremely important but sporadic discoveries of the Arabs, which for the most part vanished without results. This modern natural science dates, like our more recent history, from that mighty epoch which we Germans termed the Reformation, from the national misfortune that overtook us at that time, and which the French termed the Renaissance, and the Italians the Cinquecento, although it is not fully expressed by any of these names. It is the epoch which had its rise in the last half of the 15th century. Royalty, with the support of the burghers of the towns, broke the power of the feudal nobility and established the great monarchies. Royalty, with the support of the burghers of the towns, broke the power of the feudal nobility and established the great monarchies, based essentially on nationality, within which the modern European nations and modern bourgeois society came to development. And while the burghers and nobles were still fighting one another, the peasant war in Germany pointed prophetically to future class struggles, not only by bringing onto the stage the peasants in revolt, that was no longer anything new, but behind them the beginnings of the modern proletariat, with a red flag in their hands and the demand for common ownership of goods on their lips. In the manuscripts saved from the fall of Byzantium, and the antique statues dug out of the ruins of Rome, a new world was revealed to the astonished West. That of ancient Greece, the ghosts of the Middle Ages vanished before its shining forms. Italy rose to an undreamt of flowering of art, which seemed like a reflection of classical antiquity and was never attained again. In Italy, France, and Germany a new literature arose, the first, modern literature. Shortly afterwards came the classical epics of English and Spanish literature. The bounds of the old orbis terram were pierced. Only now for the first time was the world really discovered and the basis laid for subsequent world trade and the transition from handicraft to manufacture, which in its turn formed the starting point for modern large-scale industry. The dictatorship of the church over men's minds was shattered. It was directly cast off by the majority of the Germanic peoples, who adopted Protestantism, while among the Latins a cheerful spirit of free thought, taken over from the Arabs and nourished by the newly discovered Greek philosophy, took root more and more and prepared the way for the materialism of the 18th century. It was the greatest progressive revolution that mankind has so far experienced, a time which called for giants and produced giants, giants in power of thought, passion, and character, and universality and learning. The men who founded the modern rule of the bourgeoisie had anything but bourgeois limitations. On the contrary, the adventurous character of the time inspired them to a greater or less degree. There was hardly any man of importance then living who had not traveled extensively, who did not command 4 or 5 languages, who did not shine in a number of fields. Leonardo da Vinci was not only a great painter, but also a great mathematician, mechanician, and engineer, to whom the most diverse branches of physics are indebted for important discoveries. Albrecht Dürer was painter, engraver, sculptor, and architect, and in addition invented a system of fortification embodying many of the ideas that much later were again taken up by Montalembert and the modern German science of fortification. Machiavelli was statesman, historian, poet, and at the same time the first notable military author of modern times. Luther not only cleaned the lodge and stable of the church, but also that of the German language. He created modern German prose and composed the text and melody of the triumphal hymn which became the Marseillaise of the 16th century. The heroes of that time had not yet come under the servitude of the division of labor, the restricting effects of which, with its production of honest-sidedness, we so often notice in their successors. But what is especially characteristic of them is that they almost all pursue their lives and activities in the midst of the contemporary movements. In the practical struggle, they take sides and join in the fight, one by speaking and writing, another with the sword, many with both. Hence the fullness and force of character that makes them complete men. Men of the study are the exception, either persons of second or third rank or cautious Philistines who do not want to burn their fingers. At that time natural science also developed in the midst of the general revolution, and was itself thoroughly revolutionary. It had to win and struggle its right of existence. Side by side with the great Italians from whom modern philosophy dates, it provided its martyrs for the stake and the prisons of the Inquisition. And it is characteristic that Protestants outdid Catholics in persecuting the free investigation of nature. Calvin had Servetus burned at the stake when the latter was on the point of discovering the circulation of the blood, and indeed he kept him roasting alive during 2 hours. For the Inquisition at least it sufficed to have Giordano Bruno simply burned alive. The revolutionary act by which natural science declared its independence and, as it were, repeated Luther's burning of the papal bull was the publication of the immortal work by which Copernicus, though timidly and, so to speak, only from his deathbed, threw down the gauntlet to ecclesiastical authority in the affairs of nature. The emancipation of natural science from theology dates from this act, although the fighting out of the particular antagonistic claims has dragged out to our day and in many minds is still far from completion. Thenceforward, however, the development of the sciences proceeded with giant strides, and, it might be said, gained in force in proportion to the square of the distance from its point of departure. It was as if the world were to be shown that henceforth the reciprocal law of motion would be as valid for the highest product of organic matter, the human mind, as for inorganic substance. The main work in the first period of natural science that now opened lay in mastering the material immediately at hand. In most fields it started to be made from the very beginning. Antiquity had bequeathed Euclid and the Ptolemaic solar system. The Arabs had left behind the decimal notation, the beginnings of algebra, the modern numerals, and alchemy. The Christian Middle Ages nothing at all. Of necessity, in this situation the most fundamental natural science, the mechanics of terrestrial and heavenly bodies, occupied first place, and alongside of it, as handmaiden to it, the discovery and perfecting of mathematical methods. Great work was achieved here. At the end of the period characterized by Newton and Linnaeus we find these branches of science brought to a certain perfection. The basic features of the most essential mathematical methods were established. Analytical geometry by Descartes especially, logarithms by Napier, and the differential and integral calculus by Leibniz and perhaps Newton. The same holds good of the mechanics of rigid bodies, the main laws of which were made clear once for all. Finally, in the astronomy of the solar system, Kepler discovered the laws of planetary movement, and Newton formulated them from the point of view of the general laws of motion of matter. The other branches of natural science were far removed even from this preliminary perfection. Only towards the end of the period did the mechanics of fluid and gaseous bodies receive further treatment. Physics proper had still not gone beyond its first beginnings, with the exception of optics, the exceptional progress of which was due to the practical needs of astronomy. By the phlogistic theory, chemistry for the first time emancipated itself from alchemy. Geology had not yet gone beyond the embryonic stage of mineralogy, hence paleontology could not yet exist at all. Finally, in the field of biology the essential preoccupation was still with the collection and first sifting of the immense material, not only botanical and zoological, but also anatomical and even physiological. There could as yet be hardly any talk of the comparison of the various forms of life, of the investigation of their geographical distribution and their climatic, etc., living conditions. Here only botany and zoology arrived at an approximate completion owing to Linnaeus. But what especially characterizes this period is the elaboration of the peculiar general outlook, in which the central point is the view of the absolute immutability of nature. In whatever way nature itself might have come into being, once present it remained as it was as long as it continued to exist. The planets and their satellites, once set in motion by the mysterious first impulse, circled on and on their predestined ellipses for all eternity, or at any rate until the end of all things. The stars remain forever fixed and immovable in their places, keeping one another therein by universal gravitation. The earth had persisted without alteration from all eternity, or, alternatively, from the first day of its creation. The 5 continents of the present day had always existed, and they had always had the same mountains, valleys, and rivers, the same climate, and the same flora and fauna, except in so far as change or cultivation had taken place at the hand of man. The species of plants and animals had been established once for all when they came into existence, like continually produced like, and it was already a good deal for Linnaeus to have conceded that possibly here and there new species could have arisen by crossing. In contrast to the history of mankind, which develops in time, there was ascribed to the history of nature only an unfolding in space. All change, all development in nature, was denied. Natural science, so revolutionary at the outset, suddenly found itself confronted by an out and out conservative nature in which even today everything was as it had been at the beginning and in which, to the end of the world, or for all eternity, everything would remain as it had been since the beginning. High as the natural science of the first half of the 18th century stood above Greek antiquity and knowledge, and even in the sifting of its material, it stood just as deeply below Greek antiquity in the theoretical mastery of its material, in the general outlook on nature. For the Greek philosophers, the world was essentially something that had emerged from chaos, something that had developed, that had come into being. For the natural scientists of the period that we are dealing with, it was something ossified, something immutable, and for most of them something that had been created at one stroke. Science was still deeply enmeshed in theology. Everywhere it sought and found its ultimate resort in an impulse from outside that was not to be explained from nature itself. Even if attraction, by Newton pompously baptized as universal gravitation, was conceived as an essential property of matter, whence comes the unexplained tangential force which first gives rise to the orbits of the planets. How did the innumerable varieties of animals and plants arise? And how, above all, did man rise, since after all it was certain that he was not present from all eternity? To such questions natural science only too frequently answered by making the creator of all things responsible. Copernicus, at the beginning of the period, writes a letter renouncing theology. Newton closes the period with the postulate of a divine first impulse. The highest general idea to which this natural science attained was that of the purposiveness of the arrangements of nature, the shallow teleology of Wolff, according to which cats were created to eat mice, mice to be eaten by cats, and the whole of nature to testify to the wisdom of the creator. It is to the highest credit of the philosophy of the time that it did not let itself be led astray by the restricted state of contemporary natural knowledge, and that, from Spinoza right to the great French materialist, it insisted on explaining the world from the world itself and left the justification and detail to the natural science of the future. I include the materialists of the 18th century in this period because no natural scientific material was available to them other than the above described. Kant's epoch-making work remained a secret to them, and a place came long after them. We should not forget that this obsolete outlook on nature, although riddled through and through by the progress of science, dominated the entire first half of the 19th century, and in substance is even now still taught in all schools. The first breach in this petrified outlook on nature was made not by a natural scientist, but by a philosopher. In 1755 appeared Kant's Allgemeine Vergesichung theory de Engels. The question of the first impulse was abolished. The Earth and the whole solar system appeared as something that had come into being in the course of time. If the great majority of the natural scientists had had a little less of the repugnance to thinking that Newton expressed in the warning, physics, beware of metaphysics, they would have been compelled from the single brilliant discovery of Kant's to draw conclusions that would have spared them endless deviations and immeasurable amounts of time and labor wasted in false directions. For Kant's discovery contained the point of departure for all further progress. If the Earth were something that had come into being, then its present geological, geographical, and climatic state, and its plants and animals likewise, must be something that had come into being. It must have had a history not only of coexistence in space, but also of succession in time. If at once further investigations had been resolutely pursued in this direction, natural science would now be considerably further advanced than it is. But what good could come of philosophy? Kant's work remained without immediate results, until many years later Laplace and Herschel expounded its contents and gave them a deeper foundation, thereby gradually bringing the nebular hypothesis into favor. Further discoveries finally provided victory. The most important of these were the proper motion of the fixed stars, the demonstration of a resistant medium in universal space, the proof furnished by spectral analysis of the chemical identity of the matter of the universe and the existence of such glowing nebular masses as Kant had postulated. It is, however, permissible to doubt whether the majority of natural scientists would so soon have become conscious of the contradiction of the changing Earth that bore mutable organisms, had not the dawning conception that nature does not just exist, but comes into being and passes away, derived support from another quarter. Geology arose and pointed out, not only the terrestrial strata formed one after another and deposited one upon another, but also the shells and skeletons of extinct animals in the trunks, leaves, and fruits of no longer existing plants contained in these strata. It had finally to be acknowledged that not only the Earth as a whole, but also its present surface and the plants and animals living on it possessed a history and time. At first the acknowledgement occurred reluctantly enough. Cuvier's theory of the revolutions of the Earth was revolutionary in phrase and reactionary in substance. In place of a single divine creation, he put a whole series of repeated acts of creation, making the miracle an essential natural agent. Lyell first brought sense into geology by substituting for the sudden revolutions due to the moves of the creator the gradual effects of a slow transformation of the Earth. Lyell's theory was even more incompatible than any of its predecessors with the assumption of constant organic species. Gradual transformation of the Earth's surface and or conditions of life led directly to gradual transformation of the organisms and their adaptation to the changing environment, to the mutability of species. But tradition is a power not only in the Catholic Church, but also in natural science. For years, Lyell himself did not see the contradiction, and his pupils still less. This is only to be explained by the division of labor that had meanwhile become dominant in natural science, which more or less restricted each person to his special sphere, there being only a few whom it did not rob of a comprehensive view. Meanwhile, physics had made mighty advances, the results of which were summed up almost simultaneously by three different persons in the year 1842, an epoch-making year for this branch of natural investigation. Mayer in Auburn and Joule in Manchester demonstrated the transformation of heat into mechanical energy and of mechanical energy into heat. The determination of the mechanical equivalent of heat put this result beyond question. Simultaneously, by simply working up the separate physical results already arrived at, Grove, not a natural scientist by profession, but an English lawyer, proved that all so-called physical energy, mechanical energy, heat, light, electricity, magnetism, indeed even so-called chemical energy, become transformed into one another under definite conditions without any loss of energy occurring, and so prove post factum along physical lines Descartes' principle that the quantity of motion present in the world is constant. But that the special physical energies, the as it were immutable species of physics, were resolved into variously differentiated forms of the motion of matter, convertible into one another according to definite laws. The fortuitousness of the existence of a number of physical energies was abolished from science by the proof of their interconnections and transitions. Physics, like astronomy before it, had arrived at the result that necessarily pointed to the eternal cycle of matter in motion as the ultimate reality. The wonderfully rapid development of chemistry, since Lavoisier, and especially since Dalton, attacked the old ideas of nature from another aspect. The preparation by inorganic means of compounds that hitherto had been produced only in the living organism proved that the laws of chemistry have the same validity for organic as for inorganic bodies, and to a large extent bridged the gulf between inorganic and organic nature, a gulf that even Kant regarded as forever impassable. Finally, in the sphere of biological research, also the scientific journeys and expeditions that had been systematically organized since the middle of the previous century, the more thorough exploration of the European colonies in all parts of the world by specialists living there, and further the progress of paleontology, anatomy, and physiology in general, particularly since the systematic use of the microscope and the discovery of the cell, had accumulated so much material that the application of the comparative method became possible and at the same time indispensable. On the one hand, the conditions of life of the various floras and faunas were determined by means of comparative physical geography. On the other hand, the various organisms were compared with one another according to their homologous organs. And this not only in the adult condition, but at all stages of development. The more deeply and exactly this research was carried on, the more did the rigid system of an immutable, fixed organic nature crumble away at its touch. Not only did the separate species of plants and animals become more and more inextricably intermingled, but animals turned up, such as Amphioxus and Lepidosiren, that made a mockery of all previous classification. And finally organisms were encountered which it was not possible to say whether they belonged to the plant or animal kingdom. More and more the gaps in the paleontological record were filled up, compelling even the most reluctant to acknowledge the striking parallelism between the evolutionary history of the organic world as a whole and that of the individual organism. The Ariadne's thread was to lead the way out of the labyrinth in which botany and zoology appeared to have become more and more deeply lost. It was characteristic that, almost simultaneously with Kant's attack on the eternity of the solar system, C.F. Wolff in 1759 launched the first attack on the fixity of species and proclaimed the theory of descent. But what in his case was still only a brilliant anticipation took firm shape in the hands of Oken, Lamarck, Baer, and was victoriously carried through by Darwin in 1859, exactly 100 years later. Almost simultaneously it was established that protoplasm and the cell, which had already been shown to be the ultimate morphological constituents of all organisms, occurred independently of the lowest forms of organic life. This not only reduced the gulf between inorganic and organic nature to a minimum, but removed one of the most essential difficulties that had previously stood in the way of the theory of descent of organisms. The new conception of nature was complete in its main features. All rigidity was dissolved, all fixity dissipated, all particularity that had been regarded as eternal became transient. The whole of nature shown as moving in eternal flux and cyclical course. Thus we have once again returned to the point of view of the great founders of Greek philosophy, the view that the whole of nature, from the smallest element to the greatest, from grains of sand to suns, from protista to men, has its existence in eternal coming into being and passing away, in ceaseless flux, in unresting motion and change, only with the essential difference that what for the Greeks was a brilliant intentation, is in our case the result of strictly scientific research in accordance with experience, and hence also it emerges in a much more definite and clear form. It is true that the empirical proof of this motion is not wholly free from gaps, but these are insignificant in comparison with what has already been firmly established, and with each year they become more and more filled up. And how could the proof in detail be otherwise than defective when one bears in mind that the most essential branches of science, transplanetary astronomy, chemistry, geology, have a scientific existence of barely 100 years, and the comparative method in physiology one of barely 50 years, and that the basic form of almost all organic development, the cell, is a discovery not yet 40 years old. The innumerable suns and solar systems of our island universe, bounded by the outermost stellar rings of the Milky Way, developed from swirling, glowing masses of vapor. The laws of motion of which will perhaps be disclosed after the observations of some centuries have given us an insight into the proper motion of the stars. Obviously, this development did not proceed everywhere at the same rate. Recognition of The existence of dark bodies, not merely planetary in nature, hence extinct suns in our stellar system, more and more forces itself on astronomy. On the other hand, part of the vaporous nebular patches belong to our stellar system as suns not yet fully formed. Whereby it is not excluded that other nebulae, as Madler maintains, are distant independent island universes, the relative stage of development of which must be determined by the spectroscope. How a solar system develops from an individual nebular mass has been shown in detail by Laplace in a manner still unsurpassed. Subsequent science has more and more confirmed him. On the separate bodies so formed, suns as well as planets and satellites, the form of motion of matter at first prevailing is that which we call heat. There can be no question of chemical compounds of the elements even at a temperature like that still possessed by the sun, the extent to which heat is transformed into electricity or magnetism under such conditions. Continued solar observations will show. It is already as good as proved that the mechanical motion taking place in the sun arises solely from the conflict of heat with gravity. The smaller the individual bodies, the quicker they cool down. The satellites, asteroids, and meteors first of all, just as our moon has long been extinct. The planets cool more slowly, the central body slowest of all. With progressive cooling, the interplay of the physical forms of motion which become transformed into one another comes more and more to the forefront until finally a point is reached from when chemical affinity begins to make itself felt. The previously chemically indifferent elements become differentiated chemically one after another, obtain chemical properties, and enter into combination with one another. These compounds change continually with decreasing temperature, which affects differently not only each element but also each separate compound of the elements, changing also with the consequent passage of part of the gaseous matter first to the liquid and then the solid state, and with the new conditions thus created. The period when the planet is a firm shell and accumulations of water on its surface coincides with that when its intrinsic heat diminishes more and more in comparison to the heat emitted to it from the central body. Its atmosphere becomes the arena of meteorological phenomena in the sense in which we now understand the word. Its surface becomes the arena of geological changes in which the deposits resulting from atmospheric precipitation become of ever greater importance in comparison to the slowly decreasing external effects of the hot fluid interior. If, finally, the temperature becomes so far equalized that over a considerable portion of the surface at least it does not exceed the limits within which protein is capable of life, then, if other chemical conditions are favorable, living protoplasm is formed. What these conditions are, we do not yet know, which is not to be wondered at since so far not even the chemical formula of protein has been established. We do not even know how many chemically different protein bodies there are, and since it is only about 10 years ago that the fact became known that completely structureless protein exercises all the essential functions of life, digestion, excretion, movement, contraction, reaction to stimuli, and reproduction. Thousands of years may have passed before the conditions arose in which the next advance could take place, and this formless protein produced the first cell by formation of nucleus and cell membrane. This first cell also provided the foundation for the morphological development of the whole organic world, the first to develop, as it is permissible to assume from the whole analogy of the paleontological record, where innumerable species of non-cellular and cellular protista, of which Eozoon canidans alone has come down to us, and of which some were gradually differentiated into the first plants and others into the first animals. And from the first animals were developed, essentially by further differentiation, the numerous classes, orders, families, genera, and species of animals, and finally mammals, the form in which the nervous system attains its fullest development. And among these again finally the mammal in which nature attains consciousness of itself, man. Man too arises by differentiation, not only individually, by differentiation from a single egg cell to the most complicated organism that nature produces, no, also historically. When after thousands of years of struggle the differentiation of hand from foot and erect gait were finally established, man became distinct from the monkey and the basis was laid for the development of articulate speech and the mighty development of the brain that has since made the gulf between man and monkey an unbridgeable one. The specialization of the hand, this implies the tool, and the tool implies specific human activity, the transforming reaction of man on nature, production. Animals in the narrow sense also have tools, but only as limbs of their bodies, the ant, the bee, the beaver. Animals also produce, but their productive effect on surrounding nature in relation to the latter amounts to nothing at all. Man alone has succeeded in impressing his stamp on nature, not only by shifting the plant and animal world from one place to another, but also by so altering the aspect and climate of his dwelling place, and even the plants and animals themselves, that the consequences of his activity can disappear only with the general extinction of the terrestrial globe, and he has accomplished this primarily and essentially by means of the hand. Even the steam engine, so far his most powerful tool for the transformation of nature, depends, because it is a tool, in the last resort on the hand. But step by step with the development of the hand went that of the brain, first of all consciousness of the conditions for separate practically useful actions, and later, among the more favored peoples, and arising from the preceding, insight into the natural laws governing them. And with a rapidly growing knowledge of the laws of nature, the means for reacting on nature also grew. The hand alone would never have achieved the steam engine if the brain of man had not attained a correlative development with it, and parallel to it, and partly owing to it. With man we enter history. Animals also have a history, of their derivation and gradual evolution to their present position. This history, however, is made for them, and insofar as they themselves take part in it, this occurs without their knowledge or desire. On the other hand, the more that human beings become removed from animals in the narrow sense of the word, the more they make their own history consciously, the less becomes the influence of unforeseen effects and uncontrolled forces of this history, and the more accurately does the historical result correspond to the aim laid down in advance. If, however, we apply this measure to human history, to that of even the most developed peoples of the present day, we find that there still exists here a colossal disproportion between the proposed aims and the results arrived at, that unforeseen effects predominate, and that the uncontrolled forces are far more powerful than those set into motion according to plan. And this cannot be otherwise as long as the most essential historical activity of men, the one which has raised them from bestiality to humanity and which forms the material foundation of all their other activities, namely the production of their requirements of life. That is today social production, is above all subject to the interplay of unintended effects from uncontrolled forces and achieves its desired end only by way of exception and, much more frequently, the exact opposite. In the most advanced industrial countries we have subdued the forces of nature and pressed them into the service of mankind. We have thereby infinitely multiplied production, so that a child now produces more than 100 adults previously did. And what is the result? Increasing overwork and increasing misery of the masses, and every 10 years a great collapse. Darwin did not know what a bitter satire he wrote on mankind, and especially on his countrymen, when he showed that free competition, the struggle for existence, which the economists celebrate as the highest historical achievement, is the normal state of the animal kingdom. Only conscious organization of social production, in which production and distribution are carried on in a planned way, can lift mankind above the rest of the animal world as regards the social aspect, in the same way that production in general has done this for men in their aspect as species. Historical evolution makes such an organization daily more indispensable, but also with every day more possible. From it will take a new epoch of history, in which mankind itself, and with mankind all branches of its activity, and especially natural science, will experience an advance that will put everything proceeding in the deepest shade. Nevertheless, all that comes into being deserves to perish. Millions of years may elapse, hundreds of thousands of generations be born and die, but inexorably the time will come when the declining warmth of the sun will no longer suffice to melt the ice thrusting itself forward from the poles, when the human race, crowding more and more about the equator, will finally no longer find even enough heat for life, when gradually even the last trace of organic life will vanish, and the earth, an extinct frozen globe like the moon, will circle in deepest darkness and in an ever narrower orbit about the equally extinct sun, and at last fall into it. Other planets will have preceded it, others will follow it. Instead of the bright, warm solar system with its harmonious arrangement of members, only a cold, dead sphere will still pursue its lonely path through universal space. And what will happen to our solar system will happen sooner or later to all the other systems of our island universe. It will happen to all the other innumerable island universes, even to those the light of which will never reach the earth, while there is a living human eye to receive it. And when such a solar system has completed its life history and succumbs to the fate of all that is finite, death, what then? Will the sun's course roll on for all eternity through infinite space, and all the once infinitely diverse, differentiated natural forces pass forever into one single form of motion, attraction? Or, as Secchi asks, do forces exist in nature which can reconvert the dead system into its original state of an incandescent nebula and reawake it to new life? We do not know. At all events we do not know in the sense that we know that 2 equals 4, or that the attraction of matter increases and decreases according to the square of the distance. In theoretical natural science, however, which as far as possible builds up its view of nature into a harmonious whole, and without which nowadays even the most thoughtless empiricist cannot get anywhere, we have very often to reckon with incompletely known magnitudes, and logical consistency of thought must at all times help to get over defective knowledge. Modern natural science has had to take over from philosophy the principle of the indestructibility of motion. It cannot any longer exist without this principle. But the motion of matter is not merely crude mechanical motion, mere change of place. It is heat and light, electric and magnetic stress, chemical combination and dissociation, life and, finally, consciousness. To say that matter during the whole unlimited time of its existence has only once, and for what is an infinitesimally short period in comparison to its eternity, found itself able to differentiate its motion and thereby to unfold the whole wealth of this motion. And that before any truth remains restricted for eternity to mere change of place. This is equivalent to maintaining that matter is mortal and motion transitory. The indestructibility of motion cannot be merely quantitative. It must also be conceived qualitatively. Matter whose purely mechanical change of place includes indeed the possibility under favorable conditions of being transformed into heat, electricity, chemical action, or life. But which is not capable of producing these conditions from out of itself, such matter has forfeited motion. Motion which has lost the capacity of being transformed into the various forms appropriate to it may indeed still have dynamism, but no longer energy, and so has become partially destroyed. Both, however, are unthinkable. This much is certain. There was a time when the matter of our island universe had transformed a quantity of motion, of what kind we do not yet know, into heat, such that there could be developed from it a solar systems appertaining to at least 20 million stars. The gradual extinction of which is likewise certain. How did this transformation take place? We know just as little as Father Seti knows whether the future caput mortem of our solar system will once again be converted into the raw material of a new solar system. But here either we must have recourse to a creator, or we are forced to the conclusion that the incandescent raw material for the solar system of our universe was produced in a natural way by transformations of motion which are by nature inherent in moving matter, and the conditions of which therefore also must be reproduced by matter, even if only after millions and millions of years, and more or less by chance, but with the necessity that is also inherent in chance. The possibility of such a transformation is more and more being conceded. The view is being arrived at that the heavenly bodies are ultimately destined to fall into one another, and one even calculates the amount of heat which must be developed on such collisions. The sudden flaring up of new stars, and the equally sudden increase in brightness of familiar ones, of which we are informed by astronomy, is most easily explained by such collisions. Not only does our group of planets move about the sun, and our sun within our island universe, but our whole island universe also moves in space in temporary, relative equilibrium with the other island universes. For even the relative equilibrium of freely moving bodies can only exist where the motion is reciprocally determined, and it is assumed by many that the temperature in space is not everywhere the same. Finally, we know that, with the exception of an infinitesimal portion, the heat of the innumerable suns of our island universe vanishes into space and fails to raise the temperature of space even by millionth of a degree centigrade. What becomes of all this enormous quantity of heat? Is it forever dissipated in the attempt to heat universal space? Has it ceased to exist practically, and does it only continue to exist theoretically, in the fact that universal space has become warmer by a decimal fraction of a degree beginning with 10 or more knots? The indestructibility of motion forbids such an assumption, but it allows the possibility that by the successive falling into one another of the bodies of the universe all existing mechanical motion will be converted into heat and the latter radiated into space, so that in spite of all indestructibility of force, all motion in general would have ceased. Hence we arrive at the conclusion that in some way, which it will later be the task of scientific research to demonstrate, the heat radiated into space must be able to become transformed into another form of motion, in which it can once more be stored up and rendered active. Thereby the chief difficulty in the way of the reconversion of extinct suns into incandescent vapor disappears. For the rest, the eternally repeated succession of worlds in infinite time is only the logical complement to the coexistence of innumerable worlds in infinite space, a principle the necessity of which has forced itself even on the anti-theoretical Yankee brain of Draper. It is an eternal cycle in which matter moves, a cycle that certainly only completes its orbit in periods of time for which our terrestrial year is no adequate measure, a cycle in which the time of highest development, the time of organic life, and still more that of the life of beings conscious of nature and of themselves, is just as narrowly restricted as the space in which life and self-consciousness come into operation, a cycle in which every finite mode of existence of matter, whether it be sun or nebular vapor, single animal or genus of animals, chemical combination or dissociation, is equally transient, and where nothing is eternal but eternally changing, eternally moving matter in the laws according to which it moves and changes. But however often, and however relentlessly, this cycle is completed in time and space, however many millions of suns and earths may arise and pass away, however long it may last before the conditions for organic life develop, however innumerable the organic beings that have to arise and to pass away before animals with a brain capable of thought are developed from their midst, and for a short span of time find conditions suitable for life, only to be exterminated later without mercy. We have the certainty that matter remains eternally the same in all its transformations, that none of its attributes can ever be lost, and therefore, also, that with the same iron necessity that it will exterminate on the earth its highest creation, the thinking mind, it must somewhere else and at another time again produce it. Notes. 1. How tenaciously even in 1861 this view could be held by men whose scientific achievements had provided highly important material for abolishing it is shown by the following classic words: all the arrangements of our solar system, so far as we are capable of comprehending them, aim at preservation of what exists and unchanging continuance. Just as since the most ancient times no animal and no plant on the earth has become more perfect or in any way different, just as we find in all organisms only stages alongside one another and not following one another, just as our own race has always remained the same in corporeal respects, so even the greatest diversity in the coexisting heavenly bodies does not justify us in assuming that these forms are merely different stages of development. It is rather that everything created is equally perfect in itself. 2. The defect of Lyell's view, at least in its first form, lay in conceiving the forces at work on the earth as constant, both in quality and quantity. The cooling of the earth does not exist for him. The earth does not develop in a definite direction, but merely changes in an inconsequent fortuitous manner. 3. The multiplicity of worlds in infinite space leads to the conception of a succession of worlds in infinite time. J. W. Draper, History of the Intellectual Development of Europe, 1864. Vol. 2, p. 325. 2. Dialectics. It is, therefore, from the history of nature and human society that the laws of dialectics are abstracted, for they are nothing but the most general laws of these two aspects of historical development, as well as of thought itself, and indeed they can be reduced in the main to 3. The law of the transformation of quantity into quality and vice versa, the law of the interpretation of opposites, the law of the negation of the negation. All 3 are developed by Hegel in his idealist fashion as mere laws of thought, the first, in the first part of his logic, in the doctrine of being, the second fills the whole of the second, and by far the most important part of his logic, the doctrine of essence. Finally, the third figures as the fundamental law for the construction of the whole system. The mistake lies in the fact that these laws are foisted on nature and history as laws of thought, and not deduced from them. This is the source of the whole forced and often outrageous treatment. The universe, willy-nilly, is made out to be arranged in accordance with a system of thought which itself is only the product of a definite stage of evolution of human thought. If we turn the thing round, then everything becomes simple, and the dialectical laws that look so extremely mysterious in idealist philosophy at once become simple and clear as noonday. Moreover, anyone who is even only slightly acquainted with this Hegel will be aware that in hundreds of passages Hegel is capable of giving the most striking individual illustrations from nature and history of the dialectical laws. We are not concerned here with writing a handbook of dialectics, but only with showing that the dialectical laws are really laws of development of nature, and therefore are valid also for theoretical natural science. Hence we cannot go into the inner interconnection of these laws with one another. 1. The law of the transformation of quantity into quality and vice versa. For our purpose, we could express this by saying that in nature, in a manner exactly fixed for each individual case, qualitative changes can only occur by the quantitative addition or subtraction of matter or motion. All qualitative differences in nature rest on differences of chemical composition or on different quantities or forms of motion or, as is almost always the case, on both. Hence it is impossible to alter the quality of the body without addition or subtraction of matter or motion, that is without quantitative alteration of the body concerned. In this form, therefore, Hegel's mysterious principle appears not only quite rational, but even rather obvious. It is surely hardly necessary to point out that the various allotropic and aggregational states of bodies, because they depend on various groupings of the molecules, depend on greater or lesser quantities of motion communicated to the bodies. But what is the position in regard to change of form of motion, or so-called energy? If we change heat into mechanical motion or vice versa, is not the quality altered while the quantity remains the same? Quite correct. But it is with change of form of motion as with Heinz vices. Anyone can be virtuous by himself, for vices too are always necessary. Change of form of motion is always a process that takes place between at least two bodies, of which one loses a definite quantity of motion of one quality, while the other gains a corresponding quantity of motion of another quality. Here, therefore, quantity and quality mutually correspond to each other. So far it has not been found possible to convert motion from one form to another inside a single isolated body. We are concerned here in the first place with non-living bodies. The same law holds for living bodies, but it operates under very complex conditions, and at present quantitative measurement is still often impossible for us. If we imagine any non-living body cut up into smaller and smaller portions, at first no qualitative change occurs. But this is a limit. If we succeed, as by evaporation, in obtaining the separate molecules in the free state, then it is true that we can usually divide these still further, yet only with a complete change of quality. The molecule is decomposed into its separate atoms, which have quite different properties from those of the molecule. In the case of molecules composed of various chemical elements, atoms or molecules of these elements themselves make their appearance in the place of the compound molecule. In the case of molecules of elements, the free atoms appear, which exert quite distinct qualitative effects. The free atoms of nascent oxygen are easily able to effect what the atoms of atmospheric oxygen, bound together in the molecule, can never achieve. But the molecule is also qualitatively different from the mass of the body to which it belongs. It can carry out movements independently of this mass, and while the latter remains apparently at rest, for example heat oscillations, by means of a change of position and a connection with neighboring molecules it can change the body into an allotrope or a different state of aggregation. Thus we see that the purely quantitative operation of division has a limit at which it becomes transformed into a qualitative difference. The mass consists solely of molecules, but it is something essentially different from the molecule, just as the latter is different from the atom. It is this difference that is the basis for the separation of mechanics, as the science of heavenly and terrestrial masses, from physics, as the mechanics of the molecule, and from chemistry, as the physics of the atom. In mechanics, no qualities occur, at most, states such as equilibrium, motion, potential energy, which all depend on measurable transference of motion and are themselves capable of quantitative expression. Hence, insofar as qualitative change takes place here, it is determined by corresponding quantitative change. In physics, bodies are treated as chemically unalterable or indifferent. We have to do with changes of their molecular state and with the change of form of the motion which in all cases, at least on one of the two sides, brings the molecule into play. Here every change is a transformation of quantity into quality, a consequence of the quantitative change of the quantity of motion of one form or another that is inherent in the body or communicated to it. Thus, for instance, the temperature of water is first of all indifferent in relation to its state as a liquid. But by increasing or decreasing the temperature of liquid water, a point is reached at which this state of cohesion alters and the water becomes transformed on one side into steam and on the other into ice. Similarly, a definite minimum current strength is required to cause the platinum wire of an electric incandescent lamp to glow, and every metal has its temperature of incandescence and fusion, every liquid its definite freezing and boiling point of given pressure, insofar as our means allow us to produce the temperature required. Finally, also every gas has its critical point at which it can be liquefied by pressure and cooling. In short, the so-called physical constants are for the most part nothing but designations of the nodal points at which quantitative addition or subtraction of motion produces qualitative alteration in the state of the body concerned, at which, therefore, quantity is transformed into quality. The sphere, however, in which the law of nature discovered by Hegel celebrates its most important triumph is that of chemistry. Chemistry can be termed the science of the qualitative changes of bodies as a result of changed quantitative composition. That was already known to Hegel himself. As in the case of oxygen, if three atoms unite into a molecule, instead of the usual two, we get ozone, a body which is very considerably different from ordinary oxygen in its odor and reactions. Again, one can take the various proportions in which oxygen combines with nitrogen or sulfur, each of which produces a substance qualitatively different from any of the others. How different laughing gases from nitric and hydride. The first is a gas, the second at ordinary temperature is a solid crystalline substance. And yet the whole difference in composition is that the second contains 5 times as much oxygen as the first, and between the two of them are 3 more oxides of nitrogen, each of which is qualitatively different from the first two and from each other. This is seen still more strikingly in the homologous series of carbon compounds, especially in the simpler hydrocarbons. Of the normal paraffins, the lowest is methane, CH. Here the 4 linkages of the carbon atom are saturated by 4 atoms of hydrogen. The second, ethane, CH, has 2 atoms of carbon joined together and the 6 free linkages are saturated by 6 atoms of hydrogen. And so it goes on, with CH, etc. According to the algebraic formula CH, so that by each addition of CH a body is formed that is qualitatively distinct from the preceding one. The 3 lowest members of the series are gases. The highest known, hexadecane, CH, is a solid body with a boiling point of 270 superscript C. Exactly the same holds good for the series of primary alcohols with formula CH, derived from the paraffins, and the series of monobasic fatty acids. What qualitative difference can be caused by the quantitative addition of CH is taught by experience. If we consume ethyl alcohol, CHO, in any drinkable form without addition of other alcohols, and on another occasion take the same ethyl alcohol but with a slight addition of amyl alcohol, CHO, which forms the main constituent of the notorious fusel oil, one's head will certainly be aware of it the next morning, much to its detriment, so that one could even say that the intoxication and subsequent morning after feeling is also quantity transformed into quality, on the one hand of ethyl alcohol, and on the other hand of this added CH. In these series we encounter the Hegelian law in yet another form. The lower members permit only of a single mutual arrangement of the atoms. If, however, the number of atoms united into a molecule attains a size definitely fixed for each series, the grouping of the atoms in the molecule can take place in more than one way, so that two or more isomeric substances can be formed, having equal numbers of C, H, and 0 atoms in the molecule, but nevertheless qualitatively distinct from one another. We can even calculate how many such isomers are possible for each member of the series. Thus, in the paraffin series, for CH there are 2, for CH there are 3. Among the higher members the number of possible isomers mounts very rapidly. Hence once again it is the quantitative number of atoms in the molecule that determines the possibility and, insofar as it has been proved, also the actual existence of such qualitatively distinct isomers. Still more, from the analogy of the substances with which we are acquainted in each of these series, we can draw conclusions as to the physical properties of the still unknown members of the series and, at least for the members immediately following the known ones, predict their properties, boiling point, etc. with fair certainty. Finally, the Hegelian law is valid not only for compound substances but also for the chemical elements themselves. We now know that the chemical properties of the elements are a periodic function of their atomic weights, and that, therefore, their quality is determined by the quantity of their atomic weight. And the test of this has been brilliantly carried out. Mendeleev proved that various gaps occur in the series of related elements arranged according to atomic weights, indicating that here new elements remain to be discovered. He described in advance the general chemical properties of one of these unknown elements, which he termed aluminium, because it follows after aluminium in the series beginning with the latter, and he predicted its approximate specific and atomic weight as well as its atomic volume. A few years later, Boys-Baudouin actually discovered this element, and Mendeleev's predictions fitted with only very slight discrepancies. Aluminium was realized in gallium. By means of the unconscious application of Hegel's law of the transformation of quantity into quality, Mendeleev achieved a scientific feat which it is not too bold to put on a par with that by varying and calculating the orbit of the still unknown planet Neptune. In biology, as in the history of human society, the same law holds good at every step, but we prefer to dwell here on examples from the exact sciences, since here the quantities are accurately measurable and traceable. Probably the same gentlemen who up to now have decried the transformation of quantity into quality as mysticism and incomprehensible transcendentalism will now declare that it is indeed something quite self-evident, trivial, and commonplace, which they have long employed, and so they have been taught nothing new. But to have formulated for the first time in its universally valid form a general law of development of nature, society, and thought will always remain an act of historic importance. And if these gentlemen have for years caused quantity and quality to be transformed into one another without knowing what they did, then they will have to console themselves with Moliere's Monsieur Jourdain, who had spoken prose all his life without having the slightest inkling of it. Articles and chapters. 3. Basic forms of motion. Motion in the most general sense, conceived as the mode of existence, the inherent attribute of matter, comprehends all changes and processes occurring in the universe, from mere change of place right out to thinking. The investigation of the nature of motion, as a matter of course, to start from the lowest, simplest forms of this motion, and to learn to grasp these before it could achieve anything in the way of explanation of the higher and more complicated forms. Hence, in the historical evolution of the natural sciences, we see how first of all the theory of simplest change of place, the mechanics of heavenly bodies and terrestrial masses, was developed. It was followed by the theory of molecular motion, physics, and immediately afterwards, almost alongside of it and in some places in advance of it, the science of the motion of atoms, chemistry. Only after these different branches of the knowledge of the forms of motion governing non-living nature had attained a high degree of development could the explanation of the processes of motion represented by the life process be successfully tackled. This advanced in proportion with the progress of mechanics, physics, and chemistry. Consequently, while mechanics has for a fairly long time already been able adequately to refer to the effects in the animal body of the bony levers set into motion by muscular contraction and to the laws that prevail also in non-living nature, the physico-chemical establishment of the other phenomena of life is still pretty much at the beginning of its course. Hence, in investigating here the nature of motion, we are compelled to leave the organic forms of motion out of account. We are compelled to restrict ourselves, in accordance with the state of science, to the forms of motion of non-living nature. All motion is bound up with some change of place, whether it be change of place of heavenly bodies, terrestrial masses, molecules, atoms, or ether particles. The higher the form of motion, the smaller this change of place. It in no way exhausts the nature of the motion concerned, but it is inseparable from the motion. It, therefore, has to be investigated before anything else. The whole of nature accessible to us forms a system, an interconnected totality of bodies, and by bodies we understand here all material existence extending from stars to atoms, and be right to ether particles, insofar as one grants the existence of the last named. In the fact that these bodies are interconnected is already included that they react on one another, and it is precisely this mutual reaction that constitutes motion. It already becomes evident here that matter is unthinkable without motion. And if, in addition, matter confronts us as something given, equally uncreatable as indestructible, it follows that motion also is as uncreatable as indestructible. It became impossible to reject this conclusion as soon as it was recognized that the universe is a system, an interconnection of bodies. And since this recognition had been reached by philosophy long before it came into effective operation in natural science, it is explicable why philosophy, fully 200 years before natural science, drew the conclusion of the uncreatability and indestructibility of motion. Even the form in which it did so is still superior to the present-day formulation of natural science. Descartes' principle that the amount of motion present in the universe is always the same has only the formal defect of applying a finite expression to an infinite magnitude. On the other hand, two expressions of the same law are present current in natural science, Helmholtz's law of the conservation of force, and the newer, more precise, one of the conservation of energy. Of these, the one, as we shall see, says the exact opposite of the other, and moreover each of them expresses only one side of the relation. When two bodies act on each other so that a change of place of one or both of them results, this change of place can consist only in an approach or a separation. They either attract each other or they repel each other. Or, as mechanics expresses it, the forces operating between them are central, acting along the line joining their centers. That this happens, that it is the case throughout the universe without exception, however complicated many movements may appear to be, is nowadays accepted as a matter of course. It would seem nonsensical to us to assume, when two bodies act on each other and their mutual interaction is not opposed by any obstacle or the influence of a third body, that this action should be effected otherwise than along the shortest and most direct path. That is along the straight line joining their centers. It is well known, moreover, that Helmholtz has provided the mathematical proof that central action and unalterability of the quantity of motion are reciprocally conditioned and that the assumption of other than central actions leads to results in which motion could be either created or destroyed. Hence the basic form of all motion is approximation and separation, contraction and expansion. In short, the old polar opposites of attraction and repulsion. It is expressly to be noted that attraction and repulsion are not regarded here as so-called forces, but as simple forms of motion, just as Kant had already conceived matter as the unity of attraction and repulsion. What is to be understood by the conception of forces will be shown in due course. All motion consists of the interplay of attraction and repulsion. Motion, however, is only possible when each individual attraction is compensated by corresponding repulsion somewhere else. Otherwise, in time one side would get the preponderance over the other, and then motion would finally cease. Hence all attractions and all repulsions in the universe must mutually balance one another. Thus the law of the indestructibility and uncreatability of motion takes the form that each movement of attraction in the universe must have as its complement an equivalent movement of repulsion and vice versa. Or, as ancient philosophy, long before the natural scientific formulation of the law of conservation of force or energy, expressed it, the sum of all attractions in the universe is equal to the sum of all repulsions. However, it appears that there are still two possibilities for all motion to cease at some time or other, either by repulsion and attraction finally cancelling each other out in actual fact, or by the total repulsion finally taking possession of one part of matter and the total attraction of the other part. For the dialectical conception, these possibilities are excluded from the outset. Dialectics has proved from the results of our experience of nature so far that all polar opposites in general are determined by the mutual action of the two opposite poles on one another, that the separation and opposition of these poles exists only within their unity and interconnection, and, conversely, that their interconnection exists only in their separation and their unity only in their opposition. This once established, there can be no question of a final cancelling out of repulsion and attraction, or of a final partition between the one form of motion and one half of matter, and the other form and the other half. Consequently, there can be no question of mutual penetration, or of absolute separation of the two poles. It would be equivalent to demanding in the first case that the north and south poles of a magnet should mutually cancel themselves out, or, in the second case, that dividing a magnet in the middle between the two poles should produce on one side a north half without a south pole, and on the other side a south half without a north pole. Although, however, the impermissibility of such assumptions follows at once from the dialectical nature of polar opposites. Nevertheless, thanks to the prevailing metaphysical mode of thought of natural scientists, the second assumption at least plays a certain part in physical theory. This will be dealt with in its place. How does motion present itself in the interaction of attraction and repulsion? We can best investigate this in the separate forms of motion itself. At the end, the general aspect of the matter will show itself. Let us take the motion of a planet about its central body. The ordinary school textbook of astronomy follows Newton in explaining the ellipse described as the result of the joint action of two forces, the attraction of the central body and a tangential force driving the planet along the normal to the direction of this attraction. Thus it assumes, besides the form of motion directed centrally, also another direction of motion or so-called force perpendicular to the line joining the central points. Thereby it contradicts the above-mentioned basic law according to which all motion in our universe can only take place along the line joining the central points of the bodies acting on one another, or, as one says, is caused only by centrally acting forces. Equally, it introduces into the theory an element of motion which, as we have likewise seen, necessarily leads to the creation and destruction of motion, and therefore presupposes a creator. What had to be done, therefore, was to reduce this mysterious tangential force to a form of motion acting centrally, and this the Kant-Laplace theory of cosmogony accomplished. As is well known, according to this conception the whole solar system arose from a rotating, extremely tenuous, gaseous mass by gradual contraction. The rotational motion is obviously strongest at the equator of this gaseous sphere, and individual gaseous rings separate themselves from the mass and clump themselves together into planets, planetoids, etc., which revolve round the central body in the direction of the original rotation. This rotation itself is usually explained from the motion characteristic of the individual particles of gas. This motion takes place in all directions, but finally an excess in one particular direction makes itself evident and so causes the rotating motion, which is bound to become stronger and stronger with the progressive contraction of the gaseous sphere. But whenever hypothesis is assumed of the origin of the rotation, it abolishes the tangential force, dissolving it in a special form of the phenomena of centrally acting motion. If the one element of planetary motion, the directly central one, is represented by gravitation, the attraction between the planet and the central body, then the other tangential element appears as a relic, in a derivative or altered form, of the original repulsion of the individual particles of the gaseous sphere. Then the life process of a solar system presents itself as an interplay of attraction and repulsion, in which attraction gradually more and more gets the upper hand owing to repulsion being radiated into space in the form of heat, and thus more and more becoming lost to the system. One sees at a glance that the form of motion here conceived as repulsion is the same as that which modern physics terms energy. By the contraction of the system and the resulting detachment of the individual bodies of which it consists today, the system has lost energy, and indeed this loss, according to Helmholtz's well-known calculation, already amounts to 453,454 of the total quantity of motion originally present in the form of repulsion. Let us take now a mass in the shape of a body on our Earth itself. It is connected with the Earth by gravitation, as the Earth in turn is with the Sun, but unlike the Earth it is incapable of a free planetary motion. It can be set in motion only by an impulse from outside, and even then, as soon as the impulse ceases, its movement speedily comes to a standstill, whether by the effect of gravity alone or by the latter in combination with the resistance of the medium in which it moves. This resistance also is in the last resort an effect of gravity, in the absence of which the Earth would not have on its surface any resistant medium, any atmosphere. Hence, in pure mechanical motion on the Earth's surface we are concerned with a situation in which gravitation, attraction, decisively predominates, where therefore the production of the motion shows both phases, first counteracting gravity and then allowing gravity to act, in a word, production of rising and falling. Thus we have again mutual action between attraction on the one hand and a form of motion taking place in the opposite direction to it, hence a repelling form of motion, on the other hand. But within the sphere of terrestrial pure mechanics this repelling form of motion does not occur in nature. The physical and chemical conditions under which a lump of rock becomes separated from a mountain top or a fall of water becomes possible lie outside our sphere. Therefore, in terrestrial pure mechanics, the repelling, raising motion must be produced artificially, by human force, animal force, water or steam power, etc. And the circumstance, this necessity to combat the natural attraction artificially, causes the mechanicians to adopt the view that attraction, gravitation, or, as they say, the force of gravity, is the most important, indeed the basic, form of motion in nature. When, for instance, a weight is raised and communicates motion to other bodies by falling directly or indirectly, then according to the usual view of mechanics it is not the raising of the weight which communicates this motion but the force of gravity. Thus Helmholtz, for instance, makes the force which is the simplest and the one with which we are best acquainted, viz. gravity, act as the driving force, for instance in grandfather clocks that are actuated by weight. The weight cannot comply with the pull of gravity without setting the whole clockwork in motion, but it cannot set the clockwork in motion without itself sinking, and it goes on sinking until the string from which it hangs is completely unwound. Then the clock comes to a stop, for the operative capacity of the weight is exhausted for the time being. Its weight is not lost or diminished, it remains attracted to the same extent by the earth, but the capacity of this weight to produce movements has been lost. We can, however, wind up the clock by the power of the human arm, whereby the weight is once more raised up. As soon as this has happened, it regains its previous operative capacity and can again keep the clock in motion. According to Helmholtz, therefore, it is not the active communication of motion, the raising of the weight, that sets the clock into motion, but the passive heaviness of the weight, although the same heaviness is only withdrawn from its passivity by the raising, and once again returns to passivity after the string of the weight has unwound. If then, according to the modern conception, as we saw above, energy is only another expression for repulsion, here in the older Helmholtz conception force appears as another expression for the opposite of repulsion, for attraction. For the time being we shall simply put this on record. When this process, as far as terrestrial mechanics is concerned, has reached its end, when the heavy masses first have all been raised and then again let fall for the same height, what becomes of the motion that constituted it? For pure mechanics, it has disappeared. But we know now that it has by no means been destroyed. To a lesser extent it has been conveyed into the Earth's oscillations of sound waves, to a much greater extent into heat, which has been communicated in part to the resisting atmosphere, in part to the falling body itself, and finally in part to the floor, on which the weight comes to rest. The clock weight has also gradually given up its motion in the form of frictional heat to the separate driving wheels of the clockwork. But, although usually expressed in this way, it is not the falling motion, that is the attraction, that has passed into heat, and therefore into a form of repulsion. On the contrary, as Helmholtz correctly remarks, the attraction, the heaviness, remains what it previously was and, accurately speaking, becomes even greater. Rather it is the repulsion communicated to the raised body by rising that is mechanically destroyed by falling and reappears as heat. The repulsion of masses is transformed into molecular repulsion. Heat, as already stated, is a form of repulsion. It sets the molecules of solid bodies into oscillation, thereby loosening the connections of the separate molecules until finally the transition to the liquid state takes place. In the liquid state also, on continued addition of heat, it increases the motion of the molecules until a degree is reached at which the latter split off altogether from the mass and, at a definite velocity determined for each molecule by its chemical constitution, they move away individually in the free state. With a still further addition of heat, this velocity is further increased, and so the molecules are more and more repelled from one another. But heat is a form of so-called energy. Here once again the latter proves to be identical with repulsion. In the phenomena of static electricity and magnetism, we have a polar division of attraction and repulsion. Whatever hypothesis may be adopted of the modus operandi of these two forms of motion, in view of the facts no one has any doubt that attraction and repulsion, insofar as they are produced by static electricity or magnetism, and are able to develop unhindered, completely compensate one another, as in fact necessarily follows from the very nature of the polar division. Two poles whose activities did not completely compensate each other would indeed not be poles, and also have so far not been discovered in nature. For the time being we will leave galvanism out of account, because in its case the process is determined by chemical reactions, which makes it more complicated. Therefore, let us investigate rather the chemical processes of motion themselves. When 2 parts by weight of hydrogen combine with 15.96 parts by weight of oxygen to form water vapor, an amount of heat of 68,924 heat units is developed during the process. Conversely, if 96 parts by weight of water vapor are to be decomposed into 2 parts by weight of hydrogen and 96 parts by weight of oxygen, this is only possible on condition that the water vapor has communicated to it an amount of motion equivalent to 68,924 heat units, whether in the form of heat itself or in electrical motion. The same thing holds for all other chemical processes. In the overwhelming majority of cases, motion is given off on combination and must be supplied on decomposition. Here, too, as a rule, repulsion is the active side of the process more endowed with motion or requiring the addition of motion, while attraction is the passive side producing a surplus of motion and giving off motion. On this account, the modern theory also declares that, on the whole, energy is set free on the combination of elements and is bound up on decomposition, and Helmholtz declares this force can be conceived as a force of attraction. This force of attraction between the atoms of carbon and oxygen performs work quite as much as that exerted on a raised weight by the earth in the form of gravitation. When carbon and oxygen atoms rush at one another and combine to form carbonic acid, the newly formed particles of carbonic acid must be in very violent molecular motion, that is in heat motion. When after they have given up their heat to the environment, we still have in the carbonic acid all the carbon, all the oxygen. And in addition the affinity of both continuing to exist just as powerfully as before. But this affinity now expresses itself solely in the fact that the atoms of carbon and oxygen stick fast to one another and do not allow of their being separated. It is just as before. Helmholtz insists that in chemistry as in mechanics force consists only in attraction, and therefore is the exact opposite of what other physicists call energy, and which is identical with repulsion. Hence we have now no longer the two simple basic forms of attraction and repulsion, but a whole series of subforms in which the winding up and running down process of universal motion goes on in opposition to both attraction and repulsion. It is, however, by no means merely in our mind that these manifold forms of appearance are comprehended under the single expression of motion. On the contrary, they themselves prove in action that they are forms of one and the same motion by passing into one another under given conditions. Mechanical motion of masses passes into heat, into electricity, into magnetism. Heat and electricity pass into chemical decomposition. Chemical combination in turn develops heat and electricity and, by means of the latter, magnetism. And finally, heat and electricity produce once more mechanical movements of masses. Moreover, these changes take place in such a way that a given quantity of motion of one form always is corresponding to an exactly fixed quantity of another form. Further, it is a matter of indifference which form of motion provides the unit by which the amount of motion is measured, whether it serves for measuring mass motion, heat, so-called electromotive force, or the motion undergoing transformation in chemical processes. We base ourselves here on the theory of the conservation of energy established by J.R. Mayer in 1842 and afterwards worked out internationally with such brilliant success, and we have now to investigate the fundamental concepts nowadays made use of by this theory. These are the concepts of force, energy, and work. It has been shown above that according to the modern view, now fairly generally accepted, energy is the term used for repulsion, while Helmholtz generally uses the word force to express attraction. One could regard this as a mere distinction of form, inasmuch as attraction and repulsion compensate each other in the universe, and accordingly it would appear a matter of indifference which side of the relation is taken as positive and which as negative. Just as it is of no importance in itself whether the positive abscissae are counted to the right or the left of a point on a given line. Nevertheless, this is not absolutely so. For we are concerned here, first of all, not with the universe, but with phenomena occurring on the Earth and conditioned by the exact position of the Earth in the solar system and of the solar system in the universe. At every moment, however, our solar system gives out enormous quantities of motion into space, and motion of a very definite quality, viz. The sun's heat, repulsion. But our Earth itself allows of the existence of life on it only owing to the sun's heat, and it in turn finally radiates into space the sun's heat received, after it has converted a portion of its heat into other forms of motion. Consequently, in the solar system and above all on the Earth, attraction already considerably preponderates over repulsion. Without the repulsive motion radiated to us from the sun, all motion on the Earth would cease. If tomorrow the sun were to become cold, the attraction on the Earth would still, other circumstances remaining the same, be what it is today. As before, a stone of 100 kilograms, wherever situated, would weigh 100 kilograms. But the motion, both of masses and of molecules and atoms, would come to what we would regard as an absolute standstill. Therefore it is clear that for processes occurring on the Earth today it is by no means a matter of indifference whether attraction or repulsion is conceived as the active side of motion, hence as force or energy. On the contrary, on the Earth today attraction has already become altogether passive owing to its decisive preponderance over repulsion. We all active motion too. The supply of repulsion from the sun. Therefore, the modern school, even if it remains unclear about the nature of the relation constituting motion, nevertheless, in point of fact and for terrestrial processes, indeed for the whole solar system, is absolutely right in conceiving energy as repulsion. The expression energy by no means correctly expresses all the relationships of motion, for it comprehends only one aspect, the action but not the reaction. It still makes it appear as if energy was something external to matter, something implanted in it, but in all circumstances it is to be preferred to the expression force. As conceded on all hands, the notion of force is derived from the activity of the human organism within its environment. We speak of muscular force, of the lifting force of the arm, of the leaping power of the legs, of the digestive force of the stomach and intestinal canal, of the sensory force of the nerves, of the secretory force of the glands, etc. In other words, in order to save having to give the real cause of a change brought about by a function of our organism, we fabricate a fictitious cause, a so-called force corresponding to the change. Then we carry this convenient method over to the external world also, and so invent as many forces as there are diverse phenomena. In Hegel's time, natural science was still in this naive state, and Hegel quite correctly attacks the prevailing way of denoting forces. Similarly, in another passage, it is better that a magnet is a soul than that it has an attracting force. Force is a kind of property which is separable from matter and put forward as a predicate, while soul, on the other hand, is its movement, identical with the nature of matter. Today we no longer make it so easy for ourselves in regard to forces. Let us listen to Helmholtz. If we are fully acquainted with a natural law, we must also demand that it should operate without exception. Thus the law confronts us as an objective power, and accordingly we term it a force. For instance, we objectivize the law of the refraction of light as a refractive power of transparent substances. The law of chemical affinities is a force of affinity of the various substances for one another. Thus we speak of the electrical force of contact of metals, of the force of adhesion, capillary force, and so on. These names objectivize laws which in the first place embrace only a limited series of natural processes, the conditions for which are still rather complicated. Force is only the objectivized law of action. The abstract idea of force introduced by us only makes the addition that we have not arbitrarily invented this law, but that it is a compulsory law of phenomena. Hence our demand to understand phenomena of nature, that is to find out their laws, takes on another form of expression, viz. That we have to seek out the forces which are the causes of the phenomena. Firstly, it is certainly a peculiar manner of objectivizing if the purely subjective notion of force is introduced into a natural law that has already been established as independent of our subjectivity, and therefore completely objective. At most an old Hegelian of the strictest type might permit himself such a thing, but not a neo-Kantian like Helmholtz. Neither the law, when once established, nor its objectivity, nor that of its action, acquires the slightest new objectivity by our interpolating a force into it. What is added is our subjective assertion that it acts in virtue of some so far entirely unknown force. The secret meaning, however, of this interpolating is seen as soon as Helmholtz gives us examples: refraction of light, chemical affinity, contact electricity, adhesion, capillarity, and confers on the laws that govern these phenomenally objective, honorary rank of forces. These names objectivize laws which in the first place embrace only a limited series of natural processes, the conditions for which are still rather complicated, and it is just here that the objectivizing, which is rather subjectivizing, gets its meaning, not because we have become fully acquainted with the law, but just because this is not the case. Just because we are not yet clear about the rather complicated conditions of these phenomena, we often resort here to the word force. We express thereby not our scientific knowledge, but our lack of scientific knowledge of the nature of the law and its mode of action. In this sense, as a short expression for a causal connection that has not yet been explained, as a makeshift expression, it may pass for current usage. Anything more than that is bad. With just as much right as Helmholtz explains physical phenomena from so-called refractive force, electrical force of contact, etc. The medieval scholastics explained temperature changes by means of his calorifica and of his Fredrich, and thus save themselves all further investigation of heat phenomena. And even in this sense it is one-sided, for it expresses everything in a one-sided manner. All natural processes are two-sided. They rest on the relation of at least two effective parts, action and reaction. The notion of force, however, owing to its origin from the action of the human organism on the external world, and further because of terrestrial mechanics, implies that only one part is active, effective, the other part being passive, receptive. Hence it lays down a not yet demonstrable extension of the difference between the sexes in non-living objects. The reaction of the second part, on which the force works, appears at most as a passive reaction, as a resistance. This mode of conception is permissible in a number of fields even outside pure mechanics, namely where it is a matter of the simple transference of motion and its quantitative calculation. But already in the more complicated physical processes it is no longer adequate, as Helmholtz's own examples prove. The refractive force lies just as much in the light itself as in the transparent bodies. In the case of adhesion and capillarity, it is certain that the force is just as much situated in the surface of the solid as in the liquid. In contact electricity, at any rate, it is certain that both metals contribute to it, and chemical affinity also is situated, if anywhere, in both the parts entering into combination. But a force which consists of separated forces, an action which does not evoke its reaction, but which exists solely by itself, is no force in the sense of terrestrial mechanics, the only science in which one really knows what is meant by a force. For the basic conditions of terrestrial mechanics are, firstly, refusal to investigate the causes of the impulse, the nature of the particular force, and, secondly, the view of the one-sidedness of the force, it being everywhere opposed by identical gravitational force, such that in comparison with any terrestrial distance of fall the Earth's radius equals. But let us see further how Helmholtz objectivizes his forces into natural laws. In a lecture of 1854 he examines the store of working force originally contained in the nebulosphere from which our solar system was formed. In point of fact it received an enormously large legacy in this respect, if only in the form of the general force of attraction of all its parts for one another. This indubitably is so. But it is equally indubitable that the whole of this legacy of gravitation is present undiminished in the solar system today, apart perhaps from the minute quantity that was lost together with the matter we should now call this potential energy, which was flung out, possibly irrevocably, into space. Further, the chemical forces too must have been already present and ready to act, but as these forces could become effective only on intimate contact with the various kinds of masses, condensation had to take place before they came into play. If, as Helmholtz does above, we regard these chemical forces as forces of affinity, hence as attraction, then again we are bound to say that the sum total of these chemical forces of attraction still exists undiminished within the solar system. But on the same page Helmholtz gives us the results of his calculations that perhaps only the 454th part of the original mechanical force exists as such, that is to say, in the solar system. How is one to make sense of that? The force of attraction, general as well as chemical, is still present unimpaired in the solar system. Helmholtz does not mention any other certain source of force. In any case, according to Helmholtz, these forces have performed tremendous work, but they have neither increased nor diminished on the account. As it is with the clock weight mentioned above, so it is with every molecule in the solar system and with the solar system itself. Its gravitation is neither lost nor diminished. What happens to carbon and oxygen as previously mentioned holds good for all chemical elements. The total given quantity of each one remains, and the total force of affinity continues to exist just as powerfully as before. What have we lost then? And what force has performed the tremendous work which is 453 times as big as that which, according to his calculation, the solar system is still able to perform? Up to this point Helmholtz has given no answer, but further on he says, whether a further reserve of force in the shape of heat was present, we do not know. But, if we may be allowed to mention it, heat is a repulsive force, it acts therefore against the direction of both gravitation and chemical attraction, being minus if these are put as plus. Hence if, according to Helmholtz, the original store of force is composed of general and chemical attraction, an extra reserve of heat would have to be, not added to that reserve of force, but subtracted from it. Otherwise the sun's heat would have to strengthen the force of attraction of the earth when it causes water to evaporate in direct opposition to this attraction, and the water vapor to rise. Or the heat of an incandescent iron tube through which steam is passed would strengthen the chemical attraction of oxygen and water, whereas it puts it out of action. Or, to make the same thing clear in another form, let us assume that the nebulous sphere with radius r, and therefore with volume 4, 3r cubed has a temperature T. Let us further assume a second nebulous sphere of equal mass having at the higher temperature T the larger radius r and volume 4, 3r cubed. Now it is obvious that in the second nebulous sphere the attraction, mechanical as well as physical and chemical, can act with the same force as in the first only when it has shrunk from radius r to radius r. That is when it has radiated into the world's space heat corresponding to the temperature difference T. A hotter nebulous sphere will therefore condense later than a colder one. Consequently the heat, considered from Helmholtz's standpoint as an obstacle to condensation, is no plus but a minus of the reserve of force. Helmholtz, by presupposing the possibility of a quantum of repulsive motion in the form of heat becoming added to the attractive forms of motion and increasing the total of these latter, commits a definite error of calculation. Let us now bring the whole of this reserve of force, possible as well as demonstrable, onto the same mathematical sign so that an addition is possible. Since for the time being we cannot reverse the heat and replace its repulsion by the equivalent attraction, we shall have to perform this reversal with the two forms of attraction. Then, instead of the general force of attraction, instead of the chemical affinity, and instead of the heat, which moreover possibly already exists as such at the outset, we have simply to put the sum of the repulsive motion or so-called energy present in the gaseous sphere at the moment when it becomes independent. And by so doing Helmholtz's calculation will also hold, in which he wants to calculate the heating that must arise from the assumed initial condensation of the heavenly bodies of our system from nebulously scattered matter. By thus reducing the whole reserve of force to heat, repulsion, he also makes it possible to add on the assumed heat reserve force. The calculation then asserts that 453,454 of all the energy, that is repulsion, originally present in the gaseous sphere has been radiated into space in the form of heat, or, to put it accurately, that the sum of all attraction in the present solar system is to the sum of all repulsion, still present in the same, as 453, 1, but then it directly contradicts the text of the lecture to which it is added as proof. If then the notion of force, even in the case of a physicist like Helmholtz, gives rise to such confusion of ideas, this is the best proof that it is in general not susceptible of scientific use in all branches of investigation which go beyond the calculations of mechanics. In mechanics, the causes of motion are taken as given and their origin is disregarded, only their effects being taken into account. Hence, if a cause of motion is termed a force, this gives no damage to mechanics as such, but it becomes the custom to transfer this term also to physics, chemistry, and biology, and then confusion is inevitable. We have already seen this, and shall frequently see it again. For the concept of work, see the next chapter. Notes. 1. Helmholtz, in his Pop. Vorlesungen, 2, p. 113, appears to ascribe a certain share in the natural scientific proof of Descartes' principle of the quantitative immutability of motion to himself as well as to Mayer, Joule, and Kotlin. I myself, without knowing anything of Mayer and Kotlin, and only becoming acquainted with Joule's experiments at the end of my work, proceeded along the same path. I occupied myself especially with searching out all the relations between the various processes of nature that could be deduced from the given mode of consideration, and I published my investigations in 1847 in a little work entitled You Were Dire Had Under Craft. But, in this work there is to be found nothing new for the position in 1847 beyond the above mentioned, mathematically very valuable. Development of conservation of force and central action of the forces active between the various bodies of a system are only two different expressions for the same thing, and further a more accurate formulation of the law that the sum of the live and tensional forces in a given mechanical system is constant. In every other respect, it was already superseded since Mayer's second paper of 1845. Already in 1842 Mayer maintained the indestructibility of force, and from his new standpoint in 1845 he had much more brilliant things to say about the relations between the various processes of nature than Helmholtz had in 1847. 2. See Appendix 2, p. 881. IV. The measure of motion, work. On the other hand, I have always found hitherto that the basic concepts in this field seem very difficult to grasp for persons who have not gone through the school of mathematical mechanics, in spite of all zeal, intelligence, and even a fairly high degree of scientific knowledge. Moreover, it cannot be denied that they are abstractions of a quite peculiar kind. It was not without difficulty that even such an intellect as that of Icahn succeeded in understanding them, as is proved by his polemic against Leibniz on this subject. So says Helmholtz. According to this, we are venturing now into a very dangerous field, the more so since we cannot very well take the liberty of guiding the reader through the school of mathematical mechanics. Perhaps, however, it will turn out that, where it is a question of concepts, dialectical thinking will carry us at least as far as mathematical calculation. Galileo discovered, on the one hand, the law of falling, according to which the distances traversed by falling bodies are proportional to the squares of the times taken in falling. On the other hand, as we shall see, he put forward the not quite compatible law that the magnitude and motion of a body is determined by the mass and the velocity in such a way that for constant mass it is proportional to the velocity. Descartes adopted this latter law and made the product of the mass and the velocity of the moving body quite generally into the measure of its motion. Huygens had already found that, on elastic impact, the sum of the products of the masses, multiplied by the squares of their velocities, remains the same before and after impact, and that an analogous law holds good in various other cases of motion to a system of connected bodies. Leibniz was the first to realize that the Cartesian measure of motion was in contradiction to the law of falling. On the other hand, it could not be denied that in many cases the Cartesian measure was correct. Accordingly, Leibniz divided moving forces into dead forces and live forces. The dead were the pushes, or pulls, of resting bodies, and their measure the product of the mass and the velocity with which the body would move if it were to pass from a state of rest to one of motion. On the other hand, he put forward as the measure of the of the real motion of the body, the product of the mass and the square of the velocity. This new measure of motion he derived directly from the law of falling. The same force is required, so Leibniz concluded, to raise a body of 4 pounds in weight 1 foot as to raise a body of 1 pound in weight 4 feet, but the distances are proportional to the square of the velocity, for when a body has fallen 4 feet, it attains twice the velocity reached on falling only 1 foot. However, bodies on falling acquire the force for rising to the same height as that from which they fell, hence the forces are proportional to the square of the velocity. But he showed further that the measure of motion mv is in contradiction to the Cartesian law of the constancy of the quantity of motion, for if it was really valid the force in nature would continually increase or diminish. He even devised an apparatus which, if the measure mv were correct, would be bound to act as a perpetual mobile with continual gain of force, which, however, would be absurd. Recently, Helmholtz has again frequently employed this kind of argument. The Cartesians protested with might and main and there developed a famous controversy lasting many years, in which Kant also participated in his very first work, without, however, seeing clearly into the matter. Mathematicians today look down with a certain amount of scorn on this barren controversy which dragged out for more than 40 years and divided the mathematicians of Europe into two hostile camps, until at last D'Alembert by his trade dynamique, as it were by final verdict, put an end to the useless verbal dispute, for it was nothing else. It would, however, seem that a controversy could not rest entirely on a useless verbal dispute when it had been initiated by Leibniz against Descartes, and had occupied a man like Kant to such an extent that he devoted to it his first work, a fairly large volume. And in point of fact, how is it to be understood that motion has two contradictory measures, that on one occasion it is proportional to the velocity, and on another to the square of the velocity? Suter makes it very easy for himself. He says both sides were right and both were wrong. Nevertheless, the expression vis has endured up to the present day, only it no longer serves as a measure of force, but is merely a term that was once adopted for the product of the mass and half the square of the velocity, a product so full of significance in mechanics. Hence, mv remains the measure of motion, and vis is only another expression for mv2, concerning which formula we learn indeed that it is of great significance for mechanics, but now most certainly do not know what significance it has. Let us, however, take up the salvation-bringing trade dynamique and look more closely at D'Alembert's final verdict. It is to be found in the preface. In the text, it says, the whole question does not occur on account of l'utilité parfaite d'un styliste pour la mécanique. This is quite correct for purely mathematical mechanics, in which, as in the case of Suter above, words used as designations are only other expressions, or names, for algebraic formulae, names in connection with which it is best not to think at all. Nevertheless, since such important people have concerned themselves with the matter, he desires to examine it briefly in the preface. Clearness of thought demands that by the force of moving bodies one should understand only their property of overcoming obstacles or resisting them. Hence, force is to be measured neither by mv nor by xxx, but solely by the obstacles and resistance they offer. Now, there are, he says, 3 kinds of obstacles, insuperable obstacles, which totally destroy the motion, and for that very reason cannot be taken into account here. Obstacles whose resistance suffices to arrest the motion, and to do so instantaneously, the case of equilibrium. Obstacles which only gradually arrest the motion, the case of retarded motion. D'Alembert, however, is far too much of a philosopher not to realize that the contradiction of a twofold measure of one and the same force is not to be got over so easily. Therefore, after repeating what is basically only the same thing as Leibniz had already said, for his Eichweiler is precisely the same thing as the dead pressure of Leibniz, he suddenly goes over to the side of the Cartesians and finds the following expedient. The product mv can serve as a measure of force, even in the case of delayed motion. C dan c dernier cas on natural law force, non par law quantité absolue des obstacles, mais par la somme des resistances dix mêmes obstacles. Car on the sorry dollar q set some day resistance in the proportional à la quantité du mouvement, puisque, il a voulu tant le monde, la quantité du mouvement qui le corps peut être chaque instant, est proportional au produit de la resistance per la durée infiniment petite de l'instant. Et q la somme thesis produit est évidemment la resistance total. This latter mode of calculation seems to him the more natural one. Car on obstacle n est tel que n tant qu'il resiste et si est, a great appropriate parlor, la somme des resistances, qui est one single quote obstacle in q, Dailers, and estimate ainsi la force. On advantage des voir pour l'Eichweiler pour le movement retard down measure commune. Still, everyone can take that as he likes. And so, believing he has solved the question, by what, as Suter himself acknowledges, is a mathematical blunder, he concludes with unkind remarks on the confusion reigning among his predecessors, and asserts that after the above remarks there is possible only a very few metaphysical discussion, or still more discreditable purely verbal dispute. D'Alembert's proposal for reaching a reconciliation amounts to the following calculation. A mass 1, with velocity 1, compresses 1 spring in unit time. A mass 1, with velocity 2, compresses 4 springs, but requires 2 units of time. Only. 2 springs per unit of time. A mass 1, with velocity 3, compresses 9 springs in 3 units of time. That is only 3 springs per unit of time. Hence, if we divide the effect by the time required for it, we again come from mv to mv. This is the same argument that Catalan in particular had already employed against Leibniz. It is true that a body with velocity 2 rises against gravity 4 times as high as one with velocity 1, but it requires double the time for it. Consequently, the quantity of motion must be divided by the time. and equals 2, not equals 4. Curiously enough, this is also Suter's view, who indeed deprived the expression vis viva of all logical meaning and left it only a mathematical one. But this is natural. For Suter, it is a question of saving the formula mv and its significance as sole measure of the quantity of motion. Hence, logically, mv is sacrificed in order to rise again transfigured in the heaven of mathematics. However, this much is correct. Catalan's argument provides one of the bridges connecting mv with mv, and so is of importance. The mechanicians subsequent to D'Alembert by no means accepted his verdict, for his final verdict was indeed in favor of mv as the measure of motion. They adhere to his expression of the distinction which Leibniz had already made between dead and live forces. Mv is valid for equilibrium, that is for statics. Mv is valid for motion against resistance, that is for dynamics. Although on the whole correct, the distinction in this form has, however, logically no more meaning in the famous pronouncement of the junior officer, on duty always to me, off duty always me. It is accepted tacitly, it just exists. We cannot alter it, and if a contradiction lurks in this double measure, how can we help it? Thus, for instance, Thomson and Tate say, the quantity of motion or the momentum of a rigid body moving without rotation is proportional to its mass and velocity conjointly. Double mass or double velocity would correspond to double quantity of motion, and immediately below that they say, the vis viva or kinetic energy of a moving body is proportional to the mass and the square of the velocity conjointly. The two contradictory measures of motion are put side by side in this very glaring form. Not so much as the slightest attempt is made to explain the contradiction, or even to disguise it. In the book by these two Scotsmen, thinking is forbidden, only calculation is permitted. No wonder that at least one of them, Tate, is accounted one of the most pious Christians of pious Scotland. In Kirchhoff's Horizon Uber Mathematische Mechanik, the formula mv and mv do not occur at all in this form. Perhaps Helmholtz will aid us. In his Held Craft, he proposes to express vis viva by mv2, a point to which we shall return later. Then, on page 20 at Seek, he enumerates briefly the cases in which so far the principle of the conservation of vis viva has been recognized and made use of, included in under no, 2 is the transference of motion by incompressible solid and fluid bodies, insofar as friction or impact of inelastic materials does not occur. For these cases, our general principle is usually expressed in the rule that motion propagated and altered by mechanical powers always decreases in intensity of force in the same proportion as it increases in velocity. If, therefore, we imagine a wave being raised with velocity c by a machine in which a force for performing work is produced uniformly by some process or other, then with a different mechanical arrangement the wave nm could be raised, but only with velocity cn. So that in both cases the quantity of tensile force produced by the machine in unit time is represented by mgc, where g is the intensity of the gravitational force. Thus, here too we have a contradiction that an intensity of force, which decreases and increases in simple proportion to the velocity, has to serve as proof for the conservation of an intensity of force which decreases and increases in proportion to the square of the velocity. In any case, it becomes evident here that mv and mv serve to determine two quite distinct processes, but we certainly knew long ago that mv cannot equal mv unless v equals L. What has to be done is to make it comprehensible why motion should have a twofold measure, a thing which is surely just as unpermissible in natural sciences and commerce. Let us, therefore, attempt this in another way. By mv, then, one measures the motion propagated and altered by mechanical powers, hence this measure holds good for a lever and all its derivatives, for wheels, screws, etc., in short, for all machinery for the transference of motion. But from a very simple and by no means new consideration it becomes evident that insofar as mv applies here, so also does mv. Let us take any mechanical contrivance in which the sums of the lever arms on the two sides are related to each other as 4, 1, in which, therefore, a weight of 1 kilogram holds a weight of 4 kilograms in equilibrium. Hence, by a quite insignificant additional force on one arm of the lever we can raise 1 kilogram by 20 meters. The same additional force, when applied to the other arm of the lever, raises 4 kilograms a distance at 5 meters, and the preponderating weight sinks in the same time that the other weight requires for rising. Mass and velocity are inversely proportional to one another. mv, 1x20 equals m single quote v, 4x5. On the other hand, if we let each of the weights, after it has been raised, fall freely to the original level, then the 1 kilogram, after falling a distance of 20 meters, attains a velocity of 20 meters, the other, 4 kilograms, after falling a distance of 5 meters, attains a velocity of 10 meters. mv equals 1x20 x20 equals 400 equals m single quote v equals 4x10 x10 equals 400. On the other hand, the times of fall are different. The 4 kilograms traverse their 5 meters in 1 second. The 1 kilogram traverses its 20 meters in 2 seconds. Friction and air resistance are, of course, neglected here. But after each of the two bodies has fallen from its height, its motion ceases. Therefore, mv appears here as the measure of simple transferred, hence lasting, mechanical motion, and mv as the measure of the vanished mechanical motion. Further, the same thing applies to the impact of perfectly elastic bodies. The sum of both mv and of mv is unaltered before and after impact. Both measures have the same validity. This is not the case on impact of inelastic bodies. Here, too, the current elementary textbooks teach that before and after impact the sum of mv remains the same. On the other hand, the loss of vis viva occurs, for if the sum of mv after impact is subtracted from the sum of mv before impact, there's under all circumstances a positive remainder. By this amount the vis viva is diminished owing both to the mutual penetration and to the change of form of the colliding bodies. The latter is now clear and obvious, but not so the first assertion that the sum of mv remains the same before and after impact. In spite of Suter, vis viva is motion, and if a part of it is lost, motion is lost. Consequently, E-therm theorem directly expresses the quantity of motion, or the above assertion is untrue. In general, the whole theorem has been handed down from a period when there was as yet no inkling of the transformation of motion, when, therefore, a disappearance of mechanical motion was only conceded where there was no other way out. Thus, the equality here of the sum of mv before and after impact was taken as proved by the fact that no loss or gain of this sum had been introduced. If, however, the bodies lose vis viva and internal friction corresponding to their elasticity, they also lose velocity, and the sum of mv after impact must be smaller than before. For it is surely not possible to neglect the internal friction in calculating mv when it makes itself felt so clearly in calculating mv. But this does not matter. Even if we admit the theorem and calculate the velocity after falling, on the assumption that the sum of mv has remained the same, this decrease of the sum of mv is still found. Here, therefore, mv and mv conflict, and they do so by the difference of the mechanical motion that has actually disappeared. Moreover, the calculation itself shows that the sum of mv expresses the quantity of motion correctly, while the sum of mv expresses it incorrectly. Such are pretty nearly all the cases in which mv is employed in mechanics. Let us now glance at some cases in which mv is employed. When a cannonball is fired, it uses up in its course an amount of motion that is proportional to mv, irrespective of whether it encounters a solid target or comes to a standstill owing to air resistance and gravitation. If a railway train runs into a stationary one, the violence of the collision and the corresponding destruction is proportional to its mv. Similarly, mv serves wherever it is necessary to calculate the mechanical force required for overcoming resistance. But what is the meaning of this convenient phrase, so current in mechanics, overcoming resistance? If we overcome the resistance of gravity by raising a weight, there disappears a quantity of motion, a quantity of mechanical force, equal to that produced anew by the direct or indirect fall of the raised weight from the height reached back to its original level. The quantity is measured by half the product of the mass and the final velocity after falling, mv2. What then occurred on raising the weight? Mechanical motion, or force, disappeared as such. But it has not been annihilated, it has been converted into mechanical force of tension, to use Helmholtz's expression, into potential energy, as the moderns say, inter ergalis Clausius calls it, and this can at any moment, by any mechanically appropriate means, be reconverted into the same quantity of mechanical motion as was necessary to produce it. The potential energy is only the negative expression of the vis viva and vice versa. The 24 pounds cannonball moving with a velocity of 400 meters per second strikes the 1 meter thick armor plating of a warship, and under these conditions has apparently no effect on the armor. Consequently, an amount of mechanical motion has vanished equal to mv2, that is equals 12 x 400 x 400 x1, 2 equals 960,000 kilogram meters. What has become of it? A small portion has been expended in the concussion and molecular alteration of the armor plate. A second portion goes in smashing the cannonball into innumerable fragments. But the greater part has been converted into heat and raises the temperature of the cannonball to red heat. When the Prussians, in passing over to Nelson in 1864, brought their heavy batteries into play against the armored sides of the roll of grape, after each hit they saw in the darkness the flare produced by the suddenly glowing shot. Even earlier, Whitworth had proved by experiment that explosive shells need no detonator when used against armored warships. The glowing metal itself ignites the charge. Taking the mechanical equivalent of the unit of heat as 424 kilogram meters, the quantity of heat corresponding to the above mentioned amount of mechanical motion is 2,264 units. The specific heat of iron equals 0. 1140, that is to say, the amount of heat that raises the temperature of 1 kilogram of water by 1 superscript C suffices to raise the temperature of 0.1140 equals 8.772 kilograms of iron by 1 superscript C. Therefore, the 2,264 heat units mentioned above raise the temperature of 1 kilogram of iron by 8.772 x 2,264 equals 19,860 superscript C, or 19,860 kilograms of iron by 1 superscript C. Since this quantity of heat is distributed uniformly in the armor and the shot, the latter has its temperature raised by 19,862 x 12 equals 828 superscript O, amounting to quite a good glowing heat. But since the foremost, striking end of the shot receives at any rate by far the greater part of the heat, certainly double that of the rear half, the former would be raised to a temperature of 1,104 superscript C, and the latter to 552 superscript C, which would fully suffice to explain the glowing effect even if we make a big deduction for the actual mechanical work performed on impact. Mechanical motion also disappears in friction to reappear as heat. It is well known that, by the most accurate possible measurement of the two processes, Joule in Manchester and Codling in Copenhagen were the first to make an approximate experimental measurement of the mechanical equivalent of heat. The same thing applies to the production of an electric current in a magnetic electrical machine by means of mechanical force, for example from a steam engine. The quantity of so-called electromotive force produced in a given time is proportional to the quantity of mechanical motion used up in the same period, being equal to it if expressed in the same units. We can imagine this quantity of mechanical motion being produced, not by a steam engine, but by a wave falling in accordance with the pressure of gravity. The mechanical force that this is capable of supplying is measured by the vis viva that it would obtain on falling freely through the same distance, or by the force required to raise it against the original height, in both cases mv2. Hence we find that while it is true that mechanical motion has a two-fold measure, each of these measures holds good for a very definitely demarcated series of phenomena. If already existing mechanical motion is transferred in such a way that it remains as mechanical motion, the transference takes place in proportion to the product of the mass and the velocity. If, however, it is transferred in such a way that it disappears as mechanical motion in order to reappear in the form of potential energy, heat, electricity, etc. In short, if it is converted into another form of motion, then the quantity of this new form of motion is proportional to the product of the originally moving mass and the square of the velocity. In short, mv is mechanical motion measured as mechanical motion. mv2 is mechanical motion measured by its capacity to become converted into a definite quantity of another form of motion. And, as we have seen, these two measures, because different, do not contradict one another. It becomes clear from this that Leibniz's quarrel with the Cartesians was by no means a mere verbal dispute, and that D'Alembert's verdict in point of fact settled nothing at all. D'Alembert might have spared himself his tirades on the unclearness of his predecessors, for he was just as unclear as they were. In fact, as long as it was not known what becomes of the apparently annihilated mechanical motion, the absence of clarity was inevitable, and as long as mathematical mechanicians like Suter remain obstinately shut in by the four walls of their special science, they are bound to remain just as unclear as D'Alembert, and to put us off with empty and contradictory phrases. But how does modern mechanics express this conversion of mechanical motion into another form of motion, proportional in quantity to the former? It is performed work, and indeed a definite amount of work. But this does not exhaust the concept of work in the physical sense of the word. If, as in a steam or heat engine, heat is converted into mechanical motion, heat molecular motion is converted into mass motion. If heat breaks up a chemical compound, if it becomes converted into electricity in the thermobule, if an electric current sets free the elements of water from dilute sulfuric acid, or, conversely, if the motion produced in the chemical process of a current producing cell takes the form of electricity, and this in the circuit once more becomes converted into heat, in all these processes the form of motion that initiates the process, and which is converted by it into another form, performs work, and indeed the quantity of work corresponding to its own quantity. Work, therefore, is change of form of motion regarded in its quantitative aspect. But how so? If a raised weight remains suspended and at rest, is its potential energy during the period of rest also a form of motion? Certainly. Even Tate arrives at the conviction that potential energy is subsequently resolved into a form of actual motion. And, apart from that, Kirchhoff goes much further in saying rest is a special case of motion, and thus proves that he can not only calculate but can also think dialectically. Hence, by consideration of the two measures of mechanical motion, we arrive incidentally, easily, and almost as a matter of course, at the concept of work, which was described to us as being so difficult to comprehend without mathematical mechanics. At any rate, we now know more about it than from Helmholtz's lecture on the conservation of force, which was intended precisely to make as clear as possible the fundamental physical concepts of work and their invariability. All that we learn there about work is that it is something which is expressed in foot-pounds or in units of heat, and that the number of these foot-pounds or units of heat is invariable for a definite quantity of work, and, further, that besides mechanical forces and heat, chemical and electric forces can perform work, but that all these forces exhaust their capacity for work in the measure that they actually result in work. We learn also that it follows from this that the sum of all effective quantities of force in nature as a whole remains eternally and invariably the same throughout all the changes taking place in nature. The concept of work is neither developed nor even defined. And it is precisely the quantitative invariability of the magnitude of work which prevents him from realizing that the qualitative alteration, the change of form, is the basic condition for all physical work. And so Helmholtz can go so far as to assert that friction and elastic impact are processes in which mechanical work is destroyed and heat is produced instead. Just the contrary. Here mechanical work is not destroyed, here mechanical work is performed. It is mechanical motion that is apparently destroyed, but mechanical motion can never perform even a millionth part of a kilogram meter of work without apparently being destroyed as such, without becoming converted into another form of motion. But, as we have seen, the capacity for work contained in a given quantity of mechanical motion is what is known as its vis viva, and until recently was measured by mv, and here a new contradiction arose. Let us listen to Helmholtz. We read there that the magnitude of work can be expressed by weight m being raised to a height h, when, if the force of gravity is put as g, the magnitude of work equals mgh. For the body m to rise freely to the vertical height h, it requires a velocity v equals 2gh, and it attains the same velocity on falling. Consequently, mgh equals mv2, and Helmholtz proposes to take the magnitude mv2 as the quantity of vis viva, whereby it becomes identical with the measure of the magnitude of work. From the viewpoint of how the concept of vis viva has been applied hitherto, this change has no significance, but it will offer essential advantages in the future. It is scarcely to be believed. In 1847, Helmholtz was so little clear about the mutual relations of vis viva and work that he totally fails to notice how he transforms the former proportional measure of vis viva into its absolute measure, and remains quite unconscious of the important discovery he has made by his audacious handling, recommending his mv2 only because of its convenience as compared with mv, and it is as a matter of convenience that mechanicians have adopted mv2. Only gradually was mv2 also proved mathematically. Naumann gives an algebraical proof, Clausius, an analytical one, which is then to be met with in another form, and a different method of deduction in Kirchhoff give it. B. 27. Clerk Maxwell gives an elegant algebraical proof of the deduction of mv2 from. This does not prevent our two Scotsmen, Thomson and Tate, from asserting the vis viva or kinetic energy of a moving body is proportional to the mass and the square of the velocity conjointly. If we adopt the same units of mass as above, there is a particular advantage in defining kinetic energy as half the product of the mass and the square of the velocity. Here, therefore, we find that not only the ability to think, but also to calculate, has come to a standstill in the two foremost mechanicians of Scotland. The particular advantage, the convenience of the formula, accomplishes everything in the most beautiful fashion. For us, who have seen that vis viva is nothing but the capacity of a given quantity of mechanical motion to perform work, it is obvious on the face of it that the expression in mechanical terms of its capacity for work and the work actually performed by the latter must be equal to each other. And that, consequently, if mv2 measures the work, the vis viva must likewise be measured by mv2. But that is what happens in science. Theoretical mechanics arrives at the concept of vis viva, the practical mechanics of the engineer arrives at the concept of work and forces it on the theoreticians. And, immersed in their calculations, the theoreticians have become so unaccustomed to thinking that for years they failed to recognize the connection between the two concepts, measuring one of them by mv, the other by mv2, and finally accepting mv2 for both, not from comprehension, but for the sake of simplicity of calculation. Notes. 1. We get no further by consulting Clerk Maxwell. The latter says, work is done when resistance is overcome, and on p. 183, the energy of the body is its capacity for doing work. That is all that we learn about it. 2. The word work and the corresponding idea is derived from English engineers, but in English practical work is called work, while work in the economic sense is called labor. Hence, physical work also is termed work, thereby excluding all confusion with work in the economic sense. This is not the case in German. Therefore, it has been possible in recent pseudoscientific literature to make various peculiar applications of work in the physical sense to economic conditions of labor and vice versa. But we have also the word work, which, like the English word work, is excellently adapted for signifying physical work. Economics, however, being a sphere far too remote from our natural scientists, they will scarcely decide to introduce it to replace the word albeit, which has already obtained general currency, unless, perhaps, when it is too late. Only Clausius made the attempt to retain the expression work, at least alongside the expression albeit. Heat. As we have seen, there are two forms in which mechanical motion, vis viva, disappears. The first is its conversion into mechanical potential energy, for instance on lifting a weight. This form has the peculiarity that not only can it be retransformed into mechanical motion, this mechanical motion, moreover, having the same vis viva as the original one, but also that it is capable only of this change of form. Mechanical potential energy can never produce heat or electricity, unless it has been converted first into real mechanical motion. To use Clausius' term, it is a reversible process. The second form in which mechanical motion disappears is in friction and impact, which differ only in degree. Friction can be conceived as a series of small impacts occurring successively and side by side. Impact as friction concentrated at one spot and in a single moment of time. Friction is chronic impact. Impact is acute friction. The mechanical motion that disappears here disappears altogether as such. It can never be restored immediately out of itself. The process is not directly reversible. The motion has been transformed into qualitatively different forms of motion, into heat, electricity, into forms of molecular motion. Hence, friction and impact lead from the motion of masses, the subject matter of mechanics, to molecular motion, the subject matter of physics. In calling physics the mechanics of molecular motion, it has not been overlooked that this expression by no means covers the entire field of contemporary physics. On the contrary, ether vibrations, which are responsible for the phenomena of light and radiant heat, are certainly not molecular motions in the modern sense of the word. But their terrestrial actions concern molecules first and foremost. Refraction of light, polarization of light, etc., are determined by the molecular constitution of the bodies concerned. Similarly, almost all the most important scientists now regard electricity as a motion of ether particles. And Clausius even says of heat that in the movement of conformal atoms, the ether within the body can also participate. But in the phenomena of electricity and heat, once again it is primarily molecular motions that have to be considered. It could not be otherwise, so long as our knowledge of the ether is so small. But when we have got so far as to be able to present the mechanics of the ether, this subject will include a great deal that is now of necessity allocated to physics. The physical processes in which the structure of the molecule is altered, or even destroyed, will be dealt with later on. They form the transition from physics to chemistry. Only with molecular motion does the change of form of motion acquire complete freedom. Whereas, at the boundary of mechanics, the motion of masses can assume only a few other forms, heat or electricity. Here, a quite different and more lively capacity for change of form is to be seen. Heat passes into electricity in the thermopile. It becomes identical with light at a certain stage of radiation, and in its turn reproduces mechanical motion. Electricity and magnetism, a twin pair like heat and light, not only become transformed into each other, but also into heat and light as well as mechanical motion. And this takes place in such definite measure relations that a given quantity of any one of these forms of energy can be expressed in any other, in kilogram meters, in heat units, in volts, and similarly in a unit of measurement can be translated into any other. The practical discovery of the conversion of mechanical motion into heat is so very ancient that it can be taken as dating from the beginning of human history. Whatever discoveries, in the way of tools and domestication of animals, may have preceded it, the making of fire by friction was the first instance of men pressing a non-living force of nature into their service. Popular superstitions today still show how greatly the almost immeasurable import of this gigantic advance impressed itself on the mind of mankind. Long after the introduction of the use of bronze and iron, the discovery of the stone knife, the first tool, continued to be celebrated, all religious sacrifices being performed with stone knives. According to the Jewish legend, Joshua decreed that men born in the wilderness should be circumcised with stone knives. The Celts and Germans used stone knives exclusively in their human sacrifices, but all this long ago passed into oblivion. It was different with the making of fire by friction. Long after other methods of producing fire had become known, every sacred fire among the majority of peoples had to be obtained by friction. But even today, popular superstition in the majority of the European countries insists that fire with miraculous powers may be lighted only by means of friction. Thus, down to our own day, the grateful memory of the first great victory of mankind over nature lives on. Half unconsciously, in popular superstition, in the relics of heathen mythological recollections, among the most educated peoples in the world. However, the process of making fire by friction is still one-sided. By mechanical motion is converted into heat. To complete the process, it must be reversed. Heat must be converted into mechanical motion. Only in that case is justice done to the dialectics of the process, the cycle of the process being completed, for the first stage, at least. But history is its own pace, and however dialectical its course may be in the last analysis, dialectics has often to wait for history a fairly long time. Many thousands of years must have elapsed between the discovery of fire by friction and the time when Hero of Alexandria invented a machine which was set in rotor motion by the steam issuing from it, and almost another 2,000 years elapsed before the first steam engine was built, the first apparatus for the conversion of heat into really usable mechanical motion. The steam engine was the first really international invention, and this fact, in turn, testifies to a mighty historical advance. The Frenchman, Papin, invented the first steam engine, and he invented it in Germany. It was the German, Leibniz, scattering around him, as always, brilliant ideas, without caring whether the merit for them would be awarded him or someone else, who, as we know now from Papin's correspondence, gave him the main idea of the machine. The employment of a cylinder and piston. Soon after that, the Englishman, Savory and Newcomen, invented similar machines. Finally, their fellow countrymen, by introducing a separate condenser, brought the steam engine in principle up to the level of today. The cycle of inventions in this sphere was completed. The conversion of heat into mechanical motion was achieved. What came afterwards were improvements in details. Practice, therefore, solved after its own fashion the problem of the relations between mechanical motion and heat. It had, to begin with, converted the first into the second, and then converted the second into the first. But how did matters stand in regard to theory? The situation was pitiable enough, although it was just in the 17th and 18th centuries that innumerable accounts of travel appeared, teeming with descriptions of savages who knew no way of producing fire other than by friction, yet physicists were almost uninterested in it. They were equally indifferent to the steam engine during the whole of the 18th century and the first decades of the 19th. For the most part they were satisfied simply to record the facts. Finally, in the 20s, Sadie Carnot took the matter in hand, and indeed so very skillfully that his best calculations, afterwards presented by Clapeyron in geometrical form, have been accepted up to the present day by Clausius and Clerk Maxwell. Sadie Carnot almost got to the bottom of the question. It was not the lack of factual data that prevented him from completely solving it, but solely a preconceived false theory. Moreover, this false theory was not one which had been forced upon physicists by some variety of malicious philosophy, but was a theory contrived by the physicists themselves, by means of their own naturalistic mode of thought, so very superior to the metaphysical philosophical method. In the 17th century he was regarded, at any rate in England, as a property of bodies, as a motion of a particular kind, the nature of which has never been explained in a satisfactory manner. This is what Ch. Thomson called it, 2 years before the discovery of the mechanical theory of heat. But in the 18th century the view came more and more to the fore that heat, as also light, electricity, and magnetism, is a special substance, and that all these peculiar substances differ from ordinary matter in having no weight, in being imponderable. Notes. 1. At this time the ideas of Faraday and Maxwell were dominant, and physicists tended to regard electricity as primarily located in the field between charged bodies. 2. A body at any temperature is in equilibrium with a certain density of radiation, though very little of the energy in a given volume is in the ether, that is in the form of radiation, at ordinary temperatures. 3. See Appendix 2, pages 333-4. 4. This has certainly been verified in the sense that for modern physics the properties of particles can be regarded as essentially repulsions and attractions in the space around them, which is also full of radiation. On the other hand, the idea of ether has proved so full of internal contradictions that the word is now little used. 5. As we saw, some of the heat in a hot body takes the form of radiation. When the body gets red hot this becomes partially visible. 6. This is, of course, a mistake. The volt is not an energy unit, as Engels would soon have known had he ever had to pay an electricity bill. 7. Even Ch1-Ch5, a type of man very different physically from ourselves, possessed fire, though of course we do not know how he made it. 8. The use of fire immensely preceded domestication. 6. Electricity. Electricity, like heat, only